Bill Kovacs, and I'd like to welcome you to our building and our business and introduce the SINTERHARD metal filled project, a filament project for 3D printers. We're here in one of the 4 conference areas that we have in the building. This building is a 30,000 square foot building. It has power, 2,000 amps. It has 4 office areas. It has our computer IT center. It also has our test printers, 3D printers, our test furnaces. It has our extruders, and it also has our material and quality control lab. As we walk around today, I'm going to show you a little bit why I hope you'll join us on this little venture on how to make the SINTERHARD project part of the industrial revolution that I think is coming for 3D printing. And I don't mean 3D printing for the hobbyist or the artist, or there really is nothing wrong with that. I mean 3D printing for the industrial manufacturing concerns, and particularly the 3D printing that'll replace metal injection molding and ceramic injection molding. So let's take a walk and we'll show you the rest of the building. The SINTERHARD project is going to be something we think is really interesting in that it is following a path that began in the 70s for metal and ceramic injection molding. This path today is a $1.5 billion business in commercial parts. And in it, the metal injection molding process takes a metal powder and a thermoplastic resin, mixes them, injects it into a plastic injection molding machine, which then molds a part. The part then is a green part. The part that is then green soft with the plastic has the plastic removed either by solvent or by a thermal evaporation, and then the metal part that's left, called the brown part, is hardened by sintering. And at that point in time, you have a net-shaped part that can go to post-finishing operations like machining, coining, heat treating, surface modification, and coating. In our case, we want to follow that process almost identically and form the basis of a new industry that we think will be revolutionary in industrial manufacturing. That's the metal filament printed industry, which will make commercial parts where the 3D printer replaces the injection molding machine. Now, we think that laser sintering is a fine process, but it's expensive. Filament is the ideal way to go. Here we're building large XY Z Cartesians. We have 40 ball screws behind us, 8 foot long. These are 4 foot by 4 foot tables. They're under construction. There'll be a 8 foot ball screw in this table right here. And with that, we think the commercial part with a filament 3D printer is the route to go, as opposed to using a laser sintered process, whereby if you have an oxygen sensitive material like titanium, it is simply not going to be feasible economically to put it in a vacuum chamber. That is our expertise. I have worked in metal injection molding, making furnaces, and in these areas since the middle 80s, and I hope to bring this technology, with your help, right up to today and replace the portions of the metal injection molding process whereby the parts are legitimately can be replaced. We're now going to go to some other areas, smaller printers, material laboratories, and also our furnace area. One of the advantages we have is we own all of this equipment now. We don't have to buy anything for this process, and we've worked in this area before. So hopefully you'll allow us to work with you and get us funded to start making these filaments and get started on that interesting industrial revolution, making commercial parts. So let's move on to the next area. This is our small print test area. Obviously, we don't want to make large metal filament prints and then have to debind sinter, as we are going to be testing a lot of different filament over time and a lot of different powders and materials, along with different particle sizes and particle distributions for different material properties. These are XYZ, what I call Cartesian printers. We have 7 of these. We also have a Delta, and we have a UV resin printer, along with the ones we're building, and we have 20 different robotic devices here that are in various stages of being rebuilt, mostly being torn apart. I'm part of the team. I have a chemical engineering degree, bachelor's and master's, part of a doctor in aerospace, and business degrees in finance and marketing, along with some other strange things that I have interest in. Behind the camera is Craig, and he's trained in vacuum and thermal, has over 15 years experience in that. We have Eric, who is a licensed electrical engineer, licensed electrician in Massachusetts, and an electrical engineer. We have Larry, who is another electrical engineer, getting overloaded with electrical engineers. We have Gary, an electronics engineer and software engineer. Stephanie, Dr. Stephanie Sidney, who's a human resources, and John Gebbertson, who also is part of our people who will actually make the filament for the project. And we do intend to make this filament, and we are going to offer the filament in 2 different metals, stainless steel and aluminum, which will split the range in moderate temperature sintering and low temperature sintering, aluminum being the low temperature sintering, and 2 different plastics, ABS and PLA. ABS because it's a little bit easier material to work with in industrial environments, but you have to have a heated platform, and in bigger parts you're going to have to heat the whole thing. Whereas PLA is biodegradable, and we can get PLA in a powder form. So when we mix it at this stage, we can mix the metal and the powder very easily. We have in another part of the building, which we will see, the ability to take pellets and dry them, grind them, mix into powder. The powder has to be specific size range to be able to work. We think metal injection molding is a tougher process than the printing, mainly because you have to go and get the material flowing into all of the fingers and cavities all over through all the runners and gates. We are going to be printing 1 line at a time, and we don't have that problem. And there is some opportunity here to have some radical cost reductions yet to be realized by using a less stringent powder particle size. These are things we know in advance and why we think we are going to be a successful project if you give us the opportunity and fund us. We are also planning, once we launch this filament, to offer a tabletop debind and sinter furnace for commercial applications. Now, you need the filament to be able to debind and sinter. We have debinding and sinter furnaces, and I have built over 1,000 of these worldwide. And frankly, we think this is the necessary first step, making the SINTERHARD metal filament first, and then we will come along with non-oxide and oxide ceramic filaments, more metal powders, different particle size range, in more plastic environments. Now I'd like to take you to another area of our building to show you some of the equipment and other aspects of the process. Well, we're in our materials lab, and this is your prototype filament production area, where we can make metal and ceramic powdered filled filament for the SINTERHARD filament project. We can do it with a pellet, which is traditionally how it is done, but we will start this project using powder because we can get powder and it's easier to mix with the metal that we're going to be providing, the PLA and the ABS along with stainless and aluminum. We'll go to another area and we have a production size filament producer, and we have an intermediate size between this unit and the production size, depending on how many investors and how much material we have to produce in the next 90 days. But this will show you part of what our filament production area looks like. We also have materials test area, tensile machines, and quality control area where we have dry boxes. Now I'd like to take you to another area. Here we are in our larger warehouse area. In this area, we've got 25-foot ceilings, we've got 2,000 amps of power coming in the building, 480, 220, three-phase, 220 single-phase, and also 110. Here we have a very interesting vacuum furnace. It's very small for small test samples. It goes to 2,000 centigrade, approximately 4,000 Fahrenheit, and this brings almost all the materials we could want in a SINTERHARD filament to full final density, full final sinter porosity being closed, and you require a higher temperature in the absence of air for certain oxygen sensitive materials. Other furnaces we have, which we have in the building but we don't have to show right today for this project, we have atmosphere sintering furnaces, atmosphere vacuum debinding furnaces. We have solvent debinding furnaces. Of course, PLA will dissolve in water, which is a solvent to it, and PLA is of course biodegradable, one of the ideal materials, but indeed for commercial applications we have to look at other materials too, and ABS is among those. It's soluble in acetone and also can be thermally evaporated. Both of these thermoplastics can be recycled directly back into the program. Now, just for purposes of being within reasonable time limits, we're going to end this video on this aspect today, but on our website in the future we'll put on more video and more aspects of the project. The SINTERHARD metal filament project is just a tip of the iceberg in the materials we're proposing. We hope you'll join us in this program. We hope you'll join Eric and Craig and myself and Stephanie and Kathy and John and Gary working on this project, because it is a project that is interesting. It is a project that is going to happen, whether it happens with us or what happens to somebody else. We are going to bring it out open source so it can happen anywhere. We believe in open source, and we hope you'll join us, and you'll fund this program and we can get going and deliver you some material in the late summer. Thanks for your time. Looking forward to working with you.